I do have a couple folks with microphones on, so right now that's Nick and Ryan. If you kind of move your mouse around, if you're on a computer anyway, you move your mouse around. So sort of in the lower left, there's like a little button that sort of looks shaped like a microphone, and if you hit the button, then the background on it becomes red, and your microphone will mute. I guess it's not all that much of an issue if you, but yeah, it okay. I've got somebody who just figured out that mute button. Hope you're all doing all right. This is, I know, let's see, I'm going to count. I've got 1, 2, 3, 4, 5, 6 people joined in the room, in addition to 2 copies of myself, but it's still, it's still not the same as getting to talk to you in person. So I left so the recording is going. I have the timer here just for when class starts. As usual, I think what helps about this right now is if people can't join live, but then either watch the video later or download the video later, they'll know they can jump 200 seconds in for the real start of class. Hope you've been keeping yourself sort of busy. I don't know where you are, but here in La Crosse, the sun is shining. I did see a squirrel earlier today. I hope that just right outside, okay, behind this camera, I have a window, and I hope to see a squirrel on the fence in a moment again. This is so strange. Like, even the terrible jokes, I can't even see your rolling of eyes to the... Ah, oh my goodness. I have to admit, like, I'm oddly nervous. This really feels like the first day of class all over again, because, I mean, just really because the format is different. I'm like, I hope this works. We'll do the best that we can. We'll make the most of this. That's my goal. Hope you saw UWL's video. I was first in the thing. I didn't know they'd make me first. I'm going to mute one microphone here. Oh, no, it won't let me. Okay. 30 seconds. 30 seconds! I'll hold up for the screen here. I have a microphone that's connected. I got this for $15 on Amazon. I thought it would come in handy because if I write on this tablet over here, I wanted people to be able to let's see. Oh, cool. Yep, that's the beginning. So yeah, I noticed that if I write on the tablet in videos that I had recorded, you'd hear the clicky sound a little too much. So I think overall, in terms of format, I hope this will work out. I just now need to Okay, welcome. We'll start here. I gotta just move the timer to the other screen so that I can see how much time I've got left and all that. Um, yeah, I know this is unusual as a format. I know you didn't sign up for this, so I'm sorry that we're all experiencing what we are. I hope you'll make the most of it in this process. And I guess before we get started with the warm up, and yeah, I want to just try to make things as normal as possible in these strange circumstances. I'm here for you, so just let me know how things are going. If something's not working, let me know. If you have questions just about how class is running, or just have some concerns that are not related to this class at all, please know that I'm on your side. Okay, wait. Whew, I'm not going to do this right now. I don't even have a box of tissues that's in my office, which I can't get into right now. So class will be here as I already have some of you here. I know that I recognize that not everybody has an internet connection and can do this all the time. So or have like new obligations due to being at home. I recognize these things, but I wanted to give you an opportunity to join live because I think it makes things just a little easier on you to try to create things to be as normal as possible. You can ask questions. Just if you need to ask a question, I won't be able to hear you unless you unmute your microphone. So just like you would in class, you don't have to raise your hand. There is a feature in the system to do that. But like if I don't notice you raise your hand or you just want to ask your question, just unmute your mic and do that just like in class, Office hours will be available. Same format I had actually one student do that last week. And got help, and I can write on screen just like before, and you'll see that the Murphy Learning Center has online tutoring. So there, I just posted a link last night in Canvas to that. Make it to class if you can, but if you can't do that, the recordings will be posted. It just takes like a couple hours for the computer to process these things. There is an online quiz tomorrow, and there is a pretend online quiz as well. So the pretend online quiz is not worth points at all. I did actually pick a math question that I hope is not going to be too painful to go through, but I wanted you to just see the process. So I would just say try the pretend online quiz and then try the actual online quiz. The actual online quiz you can do anytime tomorrow. Like it's anytime from midnight to midnight, anytime on Tuesday. It's just like any of our in-class quizzes. It's meant to be a real short thing that takes 5 or 10 minutes, though you have an hour to complete it just because of the technology related issues for this. Okay, so I hope we're doing all right. I'll pause, see if we've got any just general questions or anything. Like if you have any format related things I can answer right now, let's take a moment to do that. So I'll see if anybody unmutes their mic. Okay, all right, so again, please stop me if you have any questions of any kind. The warm up I posted, I know like it's a tough. Well, let's dig into this, right? The question was, you have this function provided. Where is this thing increasing, decreasing? I know this was 2 weeks ago, so yeah, let's make the most of it. To find out where a function is increasing or decreasing, we're going to need the derivative first, okay? And then part 2 we'll do right after. So computing the derivative of and I should actually demonstrate. Here's how I point on screen. So there we go. Like that. Okay. So we'll take the derivative one term at a time, right? So we've got to take the derivative of this x to the fourth. We'll get this 4x to the third right there. And then we should take after the minus sign, take a derivative of 4x to the third, and that derivative will be 12x to the second, and this 10 is going to differentiate to 0. So in this spot that I'm pointing to right now, I didn't write a plus 0. I certainly could have. Okay, there's our derivative. And then we need to make a sign chart. I know this goes back to some things, but we need to find out the partition numbers of f prime. So we want to know where is f prime undefined and where is f prime equal to 0. So in this case, it turns out that f prime is never undefined, so f prime is always defined, because what we have here with f prime is there's no like worry about dividing by 0, no kind of issues like that. Where is f prime equal to 0? Well, why don't we just set what we just computed equal to 0? And to solve this, there are times when doing things to both sides is helpful, but for the sake of the things we're doing, I just kind of want to remind you that it's helpful to factor as much as possible. So factor out at 4x to the second, and what you'll have left in parentheses is x minus 3 equals 0. So then we can set each of these two factors here equal to 0. and I didn't show all the steps there because I wanted to save the space on the slide to do a couple other things. But you'll get, when you set 4x squared equal to 0, you're going to get x equals 0 as a solution. When you set the x minus 3 equal to 0, you add 3 to both sides, you'll get x equals 3 as a solution. So those are the only two numbers that we're going to include on a sign chart for f prime. So these x values down here, 0 and 3. The y values, that is so when you plug in 0 for x into f prime, which is over here, the number you're going to get out is a 0. Of course, the easiest way is to use this version of f prime. Same deal, if you plug in 3, this x value that's down here, into either right here or this other way of writing it right here, this 4x to the second times x minus 3, you're going to get a 0. Okay, so these zeros up here are the f prime values. They're actually slopes of tangent lines, and putting those zeros there helps, at least it helps me remind myself that there's a reason why these numbers are included here. So we know the two places where f prime is equal to 0. Now what we need to do is figure out where's f prime positive or negative for the rest of this sign chart. And so we just need to test. So we need to pick a value of x that's to the left of 0, somewhere over here. We need a value of x that's between 0 and 3. We need a value of x that's bigger than 3. Anything that's convenient. I went ahead and picked probably the same numbers that most everybody was going to pick. I chose x equals -1 for this region over there. I picked x equals 1 as the x value between 0 and 3, and I picked x equals 4 for the x value beyond 3. Just give you a moment to stare at what I did here. F prime of -1. I plugged it into this version. I'll keep highlighting over here with my pen. This 4x to the second times x minus 3. If you plug in -1, you have 4 times -1 squared. Well, when you square a thing, that part's going to be positive. Then you have this -1 minus 3. So that'll give you a less than 0 or a negative. So I'll just stop talking for a second, just give you a chance to stare at f prime of -1, f prime of 1, f prime of 4. I'd ask for a thumbs up, but I don't see most of you. So if you, I'll just wait. Get a sip of coffee. Yeah, that's my other goal, is to not, I don't want to speed up or anything like that. I want to keep a decent pace. So I hope we're doing all right. Okay. So with this negative, positive, or less than 0, bigger than 0, that information is recorded as this minus, plus. So this is a complete version of the sign chart. You've heard me say it before spring break that for your notes, and I hope if I think one of the good things to do is, I know of course these videos are recorded, you could watch them later, but the idea that you're going to watch all these videos right before the final, it's not going to happen, right? It's like, I think the video, if you've joined class live, the video is a good resource to go back to like check up on something you're rusty on. For your notes, it's helpful to actually draw this picture, then draw out this work, and then redraw a new picture. Now, you wouldn't need to spend all that time on a quiz or a test or anything, but I think it's more helpful to do that for your notes so that you see, oh yeah, what we thought about it and in what order. So this information about where, sorry, I need to just look over at my notes here. Okay, there we go. So now that we have this sign chart for f prime, we can now answer where f is increasing, decreasing, because information about f prime tells us something about f, right? So f prime, please remember, is the slope of the tangent line. So when the slope of the tangent line is negative, that means your graph has to go kind of like this, right? It can't go, it's not going this way. It's gotta, like that. And so that's the only way you get negative slopes, is what I mean. And so the minus information here and here tells us where f is decreasing. Okay, so f is decreasing for x values between -∞ and 0, so this part. And then the other place we saw a minus sign right here, those are for x values between 0 and 3. And then where is f increasing, to answer the other part of the question 1 in the warm-up, it's where we see that f prime has a plus sign. So f is increasing on the interval 3 to infinity. How are we doing so far? maybe I'll just address a question that I know that I've usually gotten about this. Feel free to ask, though, is what about zero? So some people might want to ask, hey, it looks like you just left out zero here. Isn't f decreasing at zero? And I guess I would say in a quiz or test, I wouldn't personally be too worried about it. This is a place where I'm kind of allowing some laziness of whether you include just that momentary zero or not. Technically, officially, probably what the book would say and probably what web work would say is actually because the derivative, because f prime is zero and not negative, it's actually zero. There's just like just a brief moment where f is not decreasing. F is just kind of staying in place and then decreasing again. Okay, that takes care of the first part of the question, where f is increasing, decreasing. I'd like to look at the second part of the warm-up, which is which critical numbers of f give local maxes or local mins. So the critical numbers are 0 and 3. In fact, I believe on the next slide I have copied over the sign chart. Yeah, there it is at the top. So the second piece of the warm-up. The thing that we need to recall is the first derivative test. Now, this was a long time ago. This was right before the last exam we had. So this is on that Wednesday before spring break. And I've worded it just a little different, mainly to make it fit a little better on screen. But it says if you have an x value called c that is a critical number, what do you do with that c is you look at what's going on with f prime. You really look at the sign of f prime. So if f prime starts with a negative sign and then changes to being a positive sign, then f has a local min. And then if f prime changes in sign from a positive sign to a negative sign, then f has a local max. And if f prime doesn't change in sign, then neither thing happens. And it's hard to remember all of this stuff word for word, and that's not what I'd like to do. I want to remind you, like for this thing, f prime changes from positive to negative. So to me, I draw a picture in my mind, and I'll draw this right on the slide. F prime positive is means that all those tangent lines have positive slopes. So you've got, that means the picture would have to do something like this. And then the slope is 0 for the moment, sort of at the top. And then the slope is, the tangent line slopes are negative over here. So the only way you get f prime positive then negative with 0 just for a moment, like right at the top, is like this. So it creates the shape of this peak, and that's why you have a local max. I think that's the easiest way to remember what the hell is going on with this first derivative test. But with this first derivative test in mind, it actually makes it way convenient to figure out what is going on with the critical numbers. So take a look here. We had this critical number 3, and good thing we already drew out this f prime sign chart. F prime changes from a minus sign to a plus sign. And so that's the first part of this first derivative test. We see that f has a local min at that x value 3. What about at the other x value 0? Well, f doesn't change in sign there. You'll notice that f prime is minus and then minus after as well. So because you have a minus before and after, there's no local min or local max at x equals 0. Okay, so that completes the warm-up, and just to really, again, say it because it helps connect some of the things. I think this first derivative test, I already sort of tried to draw a picture to convince you, but the thing to remember is that this is rather convincing if you just recall that f increasing is the thing that corresponds to f prime is positive, and f decreasing corresponds to f prime negative. And then that correspondence here is easiest if you just please remember that the derivative really is slope of a tangent line, or the key word being slope. Okay, so here's the thing. The new idea I want to look at today is I want to view f prime, or rather the derivative, two different ways now. I want to think about f prime as being slope and f prime as being the rate of change, because we're going to actually combine the two concepts. So in the warm-up, this is the summary of what we had. Okay, so we had this function x to the fourth minus 4x cubed plus 10. And we saw there was, just a moment ago, that there was a local min when x equals 3. And at x equals 0, there's not a local min or local max. Just because I wanted to draw a picture, so if we were to, let's say the task, because this is where we're headed throughout this week and next, is let's say we had to graph this function. Of course, we could just stick it into a graphing calculator and see what we get. But the whole point is calculus allows us to do a lot of these things in a fashion that's going to help us with a major application of calculus towards in 2 weeks from now. So to get there, we need to get familiar with graphing without using a graphing calculator. So if we needed to graph this, I would say we've got these two special x values, 0 and 3. Let's figure out what's the actual y value. So I just plugged in 0 for every, so I found that f of 0 is equal to 10. And if you plug in 3 for every x, then when x equals 3, you'll find that the y value is negative 17. So we can put all this information together. So when x equals 0, the y value is 10. So that's why there's a point drawn right there in the picture. When x equals 3, the y value is negative 17. So that's why there's this point down here. And then the other information that I still wanted to use in the picture is, okay, there's this local min when x equals 3. And so I tried to draw that in the picture, local min being this valley, right? Remember, local min was a place where that rainwater would collect. So all that information is here in the picture. Also, the fact that right here, there's no local min or local max, yeah, this spot is not a place where rainwater would collect or where a balloon would get stuck right there. So all that information is captured, but this picture is still not all that accurate. It's good, but now the new question is, how do we make this more accurate? And here's where using the second derivative becomes helpful. So again, please recall that derivative is slope, derivative is rate of change. We're going to use both of these ideas together. So what I want to do is to warm up to the idea of this, I have drawn this function and then this second function over here that I pointed arrows to both of these functions. These are both pictures of increasing. And then down here, I'm showing you two pictures of functions that are decreasing. And I would say, right, so yeah, these pictures, this picture and this picture down there, those two pictures down there are two. So I'm showing you 4 functions. And the top 2 functions are pictures of increasing. The bottom 2 functions show you pictures of decreasing functions. But they still kind of have really, honestly, different shapes to them. And if I were in class, physically in front of you, what I would do is I would take just a standard poker card, and like when you shuffle a deck of cards, like the sort of standard way of like, I don't even know if anybody, I am doing this in front of the camera. I don't know if anybody's seeing this kind of thing of like, you do this and then you kind of, once the cards have been interlaced, you kind of bend the cards the other direction, but that's what this looks like to me, right? This looks like a card bent one way and then a card bent the other direction. Same deal here. The card is sort of bent one way, and then the card is sort of bent out the other direction. So it's that kind of general thing that, like, in addition to increasing or decreasing, there's something else going on in this shape besides increasing, decreasing that we're trying to get at. These graphs bend differently. That concept is called concavity, and that's what we'll dig into right now. So the definition real quick is that f is concave up is if f prime is increasing, and f is concave down if f prime is decreasing. You could write that down if you wanted to or not. It's not the main thing I want you to actually focus on. Although this is the official definition, this is the way mathematicians would want to think of it. I think there's a better way to think of it in just a minute. So I'll save you the trouble of writing that down. And I want to dig into what the heck does this mean, concave up and concave down. The way to really handle this is to go back and recall a thing we just said a moment ago, that f increasing corresponds to f prime positive, and that f decreasing corresponds to f prime negative. Because what you can do with this, take a moment yourself, if you would please write this box down, and then in this space right over here, I'm going to have a new version of this where every f is going to get replaced with an f prime. So I'm going to over here have f prime is increasing this should correspond to, so it's like every f over here, you've got to plug in an f prime over here. So it should be f double prime is positive. Does that make sense? Give you a moment to write what the next one would be. Right? So if you took this the recall box that I have in blue, and you replaced every f with an f prime. So basically every time you see a function, you add another prime symbol. I believe you'd have this. So I hope that works for everyone. You just, in the box that's labeled recall, and there's a box that's labeled so, just replace every f with an f prime. So it's basically tacking on an extra prime everywhere. So the recall box was what we said about what does the derivative say about one function. So we can apply that to f prime itself and then learn that f double prime positive, right over here, f double prime positive corresponds to f prime increasing. Now this is useful because take a look at this. F prime increasing, this new thing, I know it corresponds to what we just said here, f double prime positive, but f prime increasing also is the text that's right up there in the definition for concave up. So we're actually going to combine several things together here. Here's how this works out now. So f is concave up, right here, it corresponds to f prime increasing. So this first correspondence just comes directly from the definition that's up at the top. And then f prime increasing corresponds to f double prime positive. That is right here. Same general deal. See if you can follow it. So f concave down, it's supposed to correspond to f prime decreasing. So that first correspondence comes from, well, right up here, right? It's literally the dictionary definition of what concave down is. And then f prime decreasing corresponds to f double prime negative. So that's right there. The key point here being, instead of remembering the definition directly, it's not the way I want you to think about it. I think the easiest thing to do is to go, wait, f concave up, I want you to correspond that to f double prime positive. So just like right before the break, we had f increasing correspond to f prime positive. Now f concave up, that corresponds to f second derivative being positive. Okay, so the first derivative positive tells you about the original function increasing. The second derivative positive tells you about the original function being concave up. Hope we're doing all right. Let's pause for questions. Anybody? Anybody? Bueller, you go and unmute a microphone. See how we're doing. Actually do have two people with their cameras on, so like I don't know, even a thumbs up or a okay. From the two people that have a camera on, I actually got thumbs up. So okay, so we're gonna then apply this, right? So what I'd like to actually do is go back to the function from the warm up to figure this out. So the just to summarize some ideas first, the derivative is slope, the derivative is rate of change. So the second derivative is the change in the slope. So we talked about how we use calculus to find out when a function is concave up or concave down, but what the heck does it look like? That's what we need to now finish off. So here's that part where I was mentioning earlier in preview that we would look at the derivative as being both a rate of change and a slope. So when you see f prime prime, I'm trying to interpret one of the primes as meaning change and one of the primes as meaning slope. That's fine, right? Like each prime either means slope or rate of change, but I want to now think about f prime prime as being the change in the slope. So what I have in this picture in this picture on the left that I just highlighted is, I know it looks like a parabola, but the key thing I want to notice about it is if you look, oh, we just had somebody join us. Okay, if you look at this function, so sorry, I hope it's visible. It is kind of in black. I've drawn a rather thin function that has that sort of shape, this smile-like shape. And what I did in the picture, because I wanted it to be clear enough over the internet, was I drew in a couple tangent lines in blue, and I tried to draw those thicker so that they were noticeable. I didn't want the tangent lines to look too long because they would run into each other. But like right here, this first blue tangent line has a negative slope, and then this next tangent line also has a negative slope, but it's not as negative. It looks like right there, I drew in a tangent line where the slope is 0, and then the slope is bigger. Right here, the slope is positive, and then the slope here is even more positive. So what I've tried to do in this picture was I tried to draw an example of a function where as you keep drawing new tangent lines, the slope of the tangent line keeps getting bigger, right? We start with negative slopes, there's a zero slope over here, and then there's a positive and even more positive, right? So it's like, I mean, these numbers are probably not completely accurate, but it's like the slope went from like a -4 to a -2.5 to a slope 0, then to like a slope, I don't know, whatever, 2, and then a slope 5, something like that, right? So the slope kept changing, and there we go. That's exactly what we're trying to talk about, the change in the slope. So if the change in the slope keeps increasing like this, that's what we have. Oh, a little typo in how I wrote concave, but that's what we'll call concave up. So this goes back to the definition that concave up was if the change in the slope is positive. Okay, and then over in the next picture we have a positive slope, and then still positive slope, but it's a smaller number, and then we have a zero slope, and then it looks like we have a negative slope, and then we have an even more negative slope. There the derivative is changing as well, right? The slope of the tangent line is changing, but the slopes of the tangent lines keep getting smaller and smaller. So that rate of change, or how is the change in the slope getting smaller and smaller, that's by definition what concave down is. So what the whole point of this is, I'm just trying to connect the definition, which seemed a little vague and abstract, to a picture. So this is a picture of what concave up looks like, and then there's a picture of what concave down looks like. An easy way to recall is that concave up, the shape is a cup, that rhymes with up. Concave down rhymes with frown. I can probably no longer use my Frozen joke, right? It's just, okay, bye. Really does not work over the interwebs as nicely. So look, the whole point is, just a slide ago, we talked about how you would take derivatives to figure out whether a function is concave up or concave down. But then what we're doing on this slide is talking about what does that even look like? So now what we can do is I just copied the pictures, the 4 pictures we had a moment ago. And earlier I had shown you 2 pictures. So those are the 2 pictures towards the top of functions that were increasing. And that's the case. So I've labeled it this way. I've said f increasing. I put this f increasing label there. But because of the way, like if these were poker cards, the way that they're kind of like if you like hold a poker card and you sort of bend it, then depending on, it'll bend one way or another. This is a picture of like half of that cup, right? So based on how this is bent, this is concave up, and then based on how this one is bent, that's a picture of concave down. Same deal, we had these 2 functions down here that showed you, so these are 2 separate functions showing you decreasing functions, but the way that the cards bend, so to speak, show this is part of that smile or that cup, concave up, and this is concave down. So we have now these 4 different types of shapes. So before break, all we would have said is, oh yeah, concave up. Or sorry, we would have just said increasing or decreasing, and that's it. But now we can like get even a little more detail by talking about concavity as well. So there's these 4 types of puzzle pieces that we'll now play with. So what I would like to do to round out this story is take the same function we had from the warm-up. Mainly because I want to work with the work that we already have. But I'd like to take this function, f of x equals x to the 4th minus 4x cubed plus 10. Same one from the warm-up, and let's find out where is this function concave up, where is this function concave down. Now the work on paper that we do first is not so bad. The real story after we do this, the more important thing is then how do we make that graph that we originally saw more accurate? All right, so concave up, concave down. It's new, so I'm not expecting you to know this first step right now, but I just, from a couple slides ago, want to remind you what we need to do is we need to talk about f double prime. Is f double prime positive? Is f double prime negative? Because that information will tell us about where f is concave up or concave down. So if we need to find out where f double prime is positive or where f double prime is negative, we should first find out where f double prime is 0. So this sounds a lot like what we did in the warm-up. In the warm-up, we made a sign chart for f prime. Now it's time to make a sign chart for f double prime. That's basically what we're going to do, right? So find out where f double prime is 0. So, okay, there's our first derivative just like from the warm-up, if you want to re-go through it, it's the derivative of x to the fourth is 4x to the third. The derivative of 4x to the third after the minus sign is a 12x to the second, and the derivative of 10 is 0. But we'll need a second derivative. So here it is, yeah, so 4x to the third, first term differentiates to become a 12x to the second. The next term of f prime is 12x to the second. When you take a derivative, you get 24 times x to the first. F double prime is always defined, but we should find out when is f double prime equal to 0. So I'll set it equal to 0. I'll set f double prime equal to 0. Same deal here. You could do things to both sides, but as much as possible, it helps us out in building the sign chart to not do that, to instead just try to factor as much as possible. The left side, you can see that a 12 factors and an x factors. So let's factor out both of those things. So I have it over here, 12x factored out, x minus 2 left in parentheses. When you set 12x equal to 0, you'll get x equals 0. When you set x minus 2 equal to 0, you get x equals 2. Okay, so those two x values are the only two x values that we'll have on an f double prime sign chart. So this is new over here. You'll notice it says f double prime on the side, not f prime, f double prime. The two x values here that we have were 0 and 2. The zeros that are above on the sign chart indicate what the value of f double prime is. So we know that f double prime is equal to 0 when x is 0. F double prime is again equal to 0 when x is equal to 2. But usual question, what happens in between? So what happens for x values between 0 and 2? What happens for x values that are to the left of 0? And what happens for x values that are beyond 2? So it's kind of like before. What we're going to do is we'll pick some x values. I should comment at this point, sometimes when people pick an x value, obviously the x value you want to pick between 0 and 2 is going to be a 1, right? But when you pick that, don't do this. Don't draw on top of that sign chart. It's a real common habit that I've seen before. The reason you don't want to do that is I won't get confused by it, but I have seen students confuse themselves because you start kind of cutting the number line in extra places, and it looks like you now need to like test what happens right there at 1.5 or something like that. So you don't want to draw like the two cuts that were drawn in right here and there. There are those two vertical tick marks at 0 and at 2. Those are the only ones you want. If you draw in more vertical tick marks, I've seen people confuse themselves and create extra work for themselves. So I'm trying to help you be lazy. Just compute values just directly underneath. Don't draw on top of that sign chart. It just gets confusing. So I'm going to use as my x values to test -1 for the x value to the left of 0. Then I'll use 1 clearly for the number between 0 and 2. And I'll use 3 for the x value. And then the version of f double prime I'm using is not the original one here, 12x squared minus 24x. You're welcome to do that. You'll get the same result as me. But this is the same thing, since we didn't do anything to both sides to get from here to here to here. We didn't do anything to both sides. So this factored version of f double prime is just much nicer. So there it is, just like in the warm-up. I'm plugging in these x values, these test numbers. I'll give you a moment to stare at that. So for instance, yeah, the first one, when you plug in -1 for all the x's, well, 12 is positive, -1 is negative, and then -1 minus 2, I don't even want to think about what actual number is, just negative, so negative times negative, that's why I have a greater than 0 here. We can use, oh yeah, I promise I'd pause, so let me make sure that give you a moment to just stare at the next two computations for f double prime of 1 and f double prime of 3. Okay, and just like when we made a sign chart for f prime, it's not the actual value of f prime, or in this case f double prime, that matters. We just want to know, is f double prime positive or negative? That's where, if you go way back to the first line of the start of our answer here, we just needed to know when f prime is positive, sorry, when f double prime is positive and when f double prime is negative. That's all we wanted to know. So that information, this greater than 0, less than 0, greater than 0, I've recorded as a plus, minus, plus in this updated sign chart. So this is a complete sign chart for f double prime. It is in fact from this complete sign chart for f double prime we can now answer the question of when is f concave up and when is f concave down. Okay, so go back to that correspondence that I had you write down. And let's see. So yeah, f is concave up. That's wherever f double prime. Oh, let me try the sentence again. Where is f concave up? That happens when f double prime is positive. And we see that positive sign right here and again over here. So those are for x values that are to the left of 0. So that's what that first interval is about. And then for x values that are bigger than 2. So that's what this second interval is about. Okay, this is where those x values represented in this interval and that interval, that's where f is concave up. Again, the important thing to say here is that information about f double prime tells you information about f. So you'll notice this is not a typo. It should say f is concave up here, not f double prime is concave up. I'm going to write a little error right now. If I put 2 tick marks there, that's not a correct statement. So it's information about f double prime that we see in the sign chart tells us information about f. That's the important thing. That's why calculus has its usefulness here. Is you take a function f, you look at f double prime, something you know about f double prime tells you information about f. Same deal to talk about where is f concave down. That's when f double prime is negative. So this minus sign that I'm pointing at currently in the sign chart, this minus sign for f double prime occurs for x values that are between 0 and 2. So f is concave down on this interval 0 to 2. So for any x value between 0 and 2, that's when f is concave down. That's when, yeah, we're done with the question. You see the smiley face. But just to talk about it, that's when, if we were to draw a better picture of this function f, for x values between 0 and 2, we should be expecting that frown-like shape. That sort of, if I do it in the camera, the shape that's like this. Okay. How are we doing for question 218? Just pause for questions. Okay. So we're done with this question, but here's what I want to do now. And I've got 17 minutes left in class. I don't think it's even going to take the whole time. Yeah, if you don't ask questions, we might end early. That's not a reason to try to end early, ever. Please ask your questions. But even though there's 17 minutes left, this next part actually takes a little bit of time. So I have to be honest, when you first start it, it's a little tedious, but I want you to practice at it and get used to it. It's kind of the task that we just kind of look at all week because I want you to get used to it this week. Is now let's take this information about this f is concave up, f is concave down. Let's also take the information from the warm-up about when f is increasing and when f is decreasing and put all this information together. So yeah, here's the new question. Take this concavity information that we just got with the f prime information, that f prime info was in the warm-up, and we'll make a better graph. So here was what we had in the warm-up. You may want to take a moment to just redraw this. As you do that, I'm going to, on my other monitor, pull up my notes. Make sure I talk about things in the appropriate order here. Okay. Okay, this is the f prime information we have. What I'm going to do, actually, is... I'll give you a little more time. I always get so excited, and I know that I remember this from in class. Like I start talking and people are still writing, and though I can't see all of you, I just wait. Okay. All right. Okay. Underneath this picture of f prime, I'm actually going to draw the f double prime sign chart we had a moment ago. But I want to be a little careful with how I draw it. So let me reveal it, and then before you draw this, let me just point out one thing, just so that you can pay attention to the same key detail. You'll notice that the 3 is here, this x value of 3, and this x value of 2, I didn't want it directly underneath. So you'll notice that though I drew this this entire sign chart directly underneath this one, where the 2 is located, it's to the left, because take a look, 3, if this wasn't a 2, if this was a 3, I would have put it right over here. But because it's a 2, I put it a little to the left. So just try to get that bit of even though you're drawing underneath, try to get the 3 kind of more to the right, the 2 to the left. Notice this x value of 0 and this x value of 0, those are aligned vertically. All right, this next part, you got to just keep your wits about you. And I did a little bit of abbreviating. I wanted to write out the word decreasing. I wanted to write out concave up, but it was going to get really messy. So here's where you've got to take, okay, f prime. I'm going to go through this step by step. I'm not going to skip any detail. So f prime is negative. That means f is decreasing. F double prime is positive. That means f is concave up. So in this region, for x values that are to the left of 0, so that's, over here, whoops, this region over there, this region over here, what should happen in the picture for f is that f should look decreasing and f should be concave up. Now the next part of the picture gets a little more confusing. So I'm going to draw in some dotted lines, which I can erase if these are getting in the way. But because the 2 here and 3, I encourage you to draw them carefully to align them. Now what I'm going to do is I'm going to lightly just draw in some dotted lines here. And the point is, in this same deal, I'm going to go ahead and just very lightly, again, okay. The whole point is, then in f, the story is rather convoluted. A lot is happening. So for between x values between 0 and 2, you need to look at this minus sign and this minus sign. The minus sign for f prime tells you f is decreasing, and the minus sign for f double prime tells you that f is concave down. I hope we're doing okay there. The next part, what happens between 2 and 3 when x is between 2 and 3? Well, so first of all, between 2 and 3, I'm pointing over here in the f prime sign chart. Where's my sign? Where's my symbol? Oh, it's this minus sign, right? So I know with the dotted whatever here in the way, it's easy to accidentally take this plus sign over here, but that plus sign was never the one that applied. That's to the right of this tick mark over here anyway. So it's this minus sign that applies. This minus sign is still the minus sign. If I get rid of these dots for a second, I think it helps. That minus sign here was the one that applied for all x values between 0 and 3. So this minus sign for f prime tells you this decreasing here. So that's true. My point is, that's true even if I draw these like lightly dotted things there, right? That this minus sign for f prime tells you f is decreasing. And then what about concave up or concave down? Now it's this plus sign over here that applies. Even with these dots that are visually distracting, I get, this plus sign is the one, this plus for f double prime is what applies, and that's why we have f is concave up there. Again, it might, for some of you, it might be easier to stare at this without all those dots in the way. So the decreasing came from this minus, while the concave up came from the plus here in the f double prime sign chart. Then after 3, increasing came from f prime positive, and then concave up came from f double prime positive. I hope we're doing overall okay there. I know that's a lot of info to take in. Again, what I'll do is maybe I'll just draw these dots in. Of course, as unfortunate things are to do this all online, one of the things you can do is if you go back and just watch like these couple minutes of the recording, you can decide for yourself whether you like to determine what's going on better with drawing in the lightly dotted things or not. But are we, I'll pause. Like, I would love to hear if anybody has a question of like, wait, how did you get Where did this CD come from, or something like those are the questions that usually come up. Okay. No, we're good. All right. I honestly think this is one of the most confusing things is piecing together all this stuff. But again, the decrease, 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 increase that you see for F came from this minus sign, and the fact that this minus sign here applied twice, right? This minus sign applies for all x values between 0 and 3 after all, so that's why there's a between 0 and 3 here. There's two pieces, and so that's why they both have a decrease. And then this plus was that increase. The plus minus plus here corresponded to concave up for the plus, concave down for that minus, and then this plus applied for both this and that, because this plus was for all x values bigger than 2. There, that's another way to try to say it. The whole point now is we need to go back to those 4 shapes that were drawn earlier, right? I had drawn for you 4 shapes, like increasing versus decreasing and concave up versus concave down, gave us 4 possible shapes, and these are what they look like if I didn't screw them up. Okay, so let's see if I have this right. Decreasing while being concave up is a picture that looks like that. Right, so the cup concave up. So the decreasing and increasing part, I think we have a more familiar handle on, but the new part is, so it's the combo of these two things. Decreasing concave up looks like this. That looks like the cup. Decreasing while concave down looks like that. So this is a picture of decreasing, but concave down looks like the frown. Here we have decreasing and concave up again. Actually, it's the same piece as right there, right? Same general shape. And then finally, we had said the last part, the shape of F should be increasing while concave up. That's a new shape. We haven't seen that one. It looks like that. Okay. So then what we should do is we should take these 4 pieces and we should draw the function. And there's one other piece of info I want to take is actually, I just want the specific points in the graph when x is 0, when x is 2, when x equals 3, because those look like special points in the graph. So all I'm going to do is I'm just going to compute them. And I did this offline, so some of these computations were actually already earlier in the slides. Like we already plugged in 0 for x to get that the y value is 10 back in the original function. We already plugged in x is 3 to get the y value is negative 17 back up here. This one's new. We had no reason during the warm-up to deal with x equals 2, but here I'm doing it. So plug in 2 over here, you'll get the y value is negative 6. So sorry I didn't show all that work, but the point is now we can draw a somewhat more accurate picture. So I'm going to try to do this here. So first f of 0 equals 10. So you've got this point here, 0, comma 10. Where should I label this? Maybe like right there. Okay, there's that point. F of, let's just call that 1. Let's call this 2. So f of 2 is negative 6. So there's a point that's right there. So you could either label the axes as I did or do a thing like this, 2 comma negative 6. And then when you have x is 3, the y value is negative 17. So negative 17 is a point that's right there. So 3 comma negative 17. Okay, so the graph that we need to draw should go through these 3 points specifically that were just drawn. But in addition, we have these 4 shapes. And I like to think of this like playing Legos. It's like these, we need to draw a shape that looks like this one to the left of 0. So that means like that, right? And then after, we should snap a Lego piece that looks like this into a Lego piece that looks like that, right? So think about like how this, I'm going to highlight it on my slide there. That end, imagine like that's where like a Lego connector is and connect it to this. But do that over here. So can I have you take a moment, like on paper somewhere? I would like you to take your own guess, please, at this process. If you would treat these like 4 Lego pieces. I mean, I'm going to do this in a moment, but I think it's good if you give it a try to think about connecting that point to this one, and then this end of the Lego piece to that, and then this end of the Lego piece to that. And of course, the graph should go through these special points there. Okay, so this next Lego piece, this one I just circled, it's the part, that's what the graph is supposed, that's the general shape we're supposed to have for x between 0 and 2. So it should, there's that Lego piece. It's stretched out a little bit more than obviously it's shown right there. And then this next Lego piece, so something, oh, it's getting in the way of how I labeled the point, but well, that happens sometimes. And then the last Lego piece, the piece that looks like this. So this, generally speaking, ought to be the graph of the function, right? It's not perfectly accurate, but this is the idea. How are we doing so far? Is this kind of working for folks? Okay, we're so close to done. What I just want to do is I want to point out that this, if you go back to the beginning, we drew a picture that wasn't all that accurate, but this is a much more accurate picture. What I'm going to do is click on this link, and it will probably open in the wrong window. So yeah, it's loading. I'll just do that. And as Desmos does its thing, oh, come on. This is unfortunate. This shouldn't take up much. This should be just like in class. Come on. Well, that's fun. Okay, well, you know what? I'll have you click on that link later. The whole point is the picture that we drew is actually rather... Oh, here it is. Now it's showing up. Okay. So I first of all, just to start, drew in these 3 points, and then the pieces, I just had the computer draw them in separately. So you can see those 4 Lego pieces. So this is a completely accurate picture. The one we, of course, drew wasn't perfect. And then here's the whole thing kind of all at once, now shown in green. But that's actually, I think, fairly accurate to the drawing that we just did. Okay, last little thing. Oh, so here's just directly in the slides, I asked the computer to draw an accurate version of this. The one last thing I want to say today, and we'll continue on it tomorrow, is there's this concept called an inflection point. So an inflection point is a point where there's a transition between concave up and concave down. So if in your picture of F, there's concave up and then there's a change into concave down, that's where you have an inflection point. So that, of course, if this is what it means for F, then it says something about F double prime. So if F double prime changes in sign from positive to negative or negative to positive, you have an inflection point. So what I'd like to do is let's find, sorry, it says answer here, but there's not really a question. This is more an example, is maybe the way to say it. So earlier we had this information for F, and there's a change in concavity that occurs, let's see right here. Yeah, concave up changes to become concave down. So right at the x value 0, that's where there's going to be an inflection point. Again, there's a concave down, then change to concave up. So there's another inflection point there. So when x equals 0 and when x equals 2, those are where you have inflection points. Now, the one thing I should point out is that an inflection point is a point. And so that's why I wrote these as points. So that's why there's an x coordinate 0 and a y coordinate 10. The y coordinate -6 as well. Those are just numbers we computed a moment ago. The key point here being that when you, if we just talk about the x coordinates for the inflection points, right at 0 and right at 2, that's where you see a change from CU to CD or vice versa. So that's where we have these 2 inflection points. That's all I really wanted to say for the day. Again, this is the same announcement in case I had students join our class a little late today. I'm on your side. Let me know what I can do to make this work for you. I will upload the videos as soon as I finish the next section as well. Please try the pretend quiz. I think that's maybe the main thing I want to say is try the pretend quiz sometime today, tomorrow, and then try the actual quiz tomorrow. And I'll have class like this. I'll have office hours. The Murphy Learning Center has tutoring. And slides, as always, are available in Canvas as well. So I think I'll end it with that. and see you tomorrow.